2 electrons per orbital. So you can only put 2 electrons in a single orbital. So for the S, since you have only, so here, this is S, we say how many orbitals, let's say the number of orbitals. And the number of electrons. Well, for S, we only have 1 orbital, so that's only 2 electrons. For P, we have 3 orbitals. Remember, we discussed that last time, and that is 6. For D, that's 5 orbitals, and that's 10. So you just multiply it by 2. And for F, you have 7 orbitals, so that's 14 electrons. So it's 1, 3, 5, 7, increases by 2, go from 1 to 3 to 5 to 7, and correspondingly, the electrons will increase by 4 because you have more spaces now. So think of those orbitals as, again, compartments in the atom, and the electrons occupy them. Now, when it comes to the energies of the orbitals, remember you have energy levels. So you have the first energy level, the ground state, second energy level, the third energy level. You can think of those as floors in a building, and you can think of the orbitals as rooms. So as you go up, let's say you're going to have more rooms. Let's say this is a kind of, generally this is true for, let's say, some buildings, where the first floor is, the lounge and the hallway. So there's only like one big room. It's not that crowded. And then, when you go up, you're going to have more and more rooms. So think of it that way. So very well, when it comes to the energies of the orbitals, it says in many electron greater than hydrogen atoms, repulsions caused by electrons cause different subshells, the S, the P, the D, all of those, to be at different energy levels. Electrons are negatively charged, so they actually repel each other. So therefore, they want to move away from each other, and that actually ends up changing the energy, increases the energy. The key idea, and this is, please pay attention to this, the key idea is that in many electron atom, for a given value of n, the energy of an orbital increases with the increasing value of L. So remember, when L is 0, that's an S. When it's a 1, that's a P. When it's a 2, it's a D. And then when it's a 3, it's an F. So it says to you, for a given value of n. So if n is 1, then it always, let's say n is 3 or 4 when we have them all. Then it always starts with S, then P, then D, then F. That's the order. But again, here's a common mistake. Certain people, or some students again, think that P will always be above the S no matter what. It will be above it at the same energy level. So think of it as those rooms that have to be occupied. If you have a floor and you have the S on it, you go, that's what's occupied first. Then you go to the P, then the D, in that same floor. After this is full, then you go to the next floor. But you can't jump, let's say, from the S in the first floor to the S in the second floor, and then, miss the P and the D, all that stuff that's also found on the same energy level. So look at it here. This is a great representation. So it shows you that, okay, since we have only the ground state, there's only one subshell. Here it is, very low in energy. When you have a second energy level, you have 2 subshells. You have the 2s and the 2p. And when you have a third energy level, now you have the 3s, the 3p, and the 3d. And you see these as the number of orbitals. And then the 4s, then the 4p, then of course you have the 4d, so on and so forth. But notice how it's consistent. Yes, there's an anomaly here, and welcome to science, because that's how science is always surprising in some sense. Nature is very surprising. The 4s and the 3d, to some people may kind of like say, okay, well, why is the 4s less if it's at a different energy level? Well, we'll get to that. That's an exception. So again, notice how at the second energy level, S is lower than P. So we're going to say this is the ground state. So that's N equals 1. This is the second energy level. That's N equals 2. And I'm just going to put, N equals 3 for these, all of these, including the D. And this is N equals 4 for these. Of course, we're not showing the D and F because, again, it's just, it follows. That's the consistency here. So this brings us to electron configuration. And electron configuration, it's a very important topic. And what it does, electron configuration, and let me just increase it here. All it is that if you were to ask somebody, imagine you have an analogy. Imagine someone wants to get a report on the tenants in a building. You get back the report and it says to you, okay, in this report you have 2 people in the first floor, 8 people in the second floor, 18 people in the third floor, so on and so forth. Imagine we want to do the same thing for the atom. So we would like to know, well, which atom, and in this atom, which orbitals are occupied and how many electrons are there? Okay, so it always goes like this. It always goes like this. You're going to have N, that's the period number or the principal quantum number, the energy level. You're going to have L, which is going to be either the S, the P, the D, and the F. And you're going to have a number on the top. And that right there is the number of electrons. This is the energy level. So I'm going to give you an example of this. If I say I have 1s1, that is the ground state. That is the s orbital. And that is 1 electron. If I have something like, 1s2, 2s2, 2p6, so on and so forth, again, you can see that all of those numbers, the front numbers are n, and then the s's are L, but notice that this S is at the first energy level, this is at the second energy level, this is now a P, so on and so forth. So notice that you can put more electrons in P because you have more orbitals. The pattern of filling, of orbital filling, that reflects what you have just learned is known as, it's a German word, it's the Aufbau principle, which means build up or building up. You start from most stable orbital and you go all the way to the outer. You start from the inner to the outer. Very important. The S sublevel or subshell has only 1 orbital and can therefore hold only 2 electrons. The P sublevel has 3 orbitals and can hold 6 electrons. As we said before, D can take 10 because you have 5 orbitals, and then F can take 14 because you have 7. We already talked about this. Before we begin, you're going to need your periodic table. So if you have your periodic table out, if you have a fresh copy, you have one on the computer, you're going to need it because I'm going to show you the process doing it. But what I want to do, I want to show you is generally, it's anytime, let's say, you have an electron configuration. Once again, it's going to be N. That's the period number or the energy level. Okay, let's say you have an S. The most you can have is 2. Okay, let's say, what follows, I don't know, in that case is a P. Well, you have N at, let's say, the same energy level. Again, you're going to see that. Just bear with me. And then P can only go up to 6. If you have N and then D, and let me take this. Let me go back to this. Because this is important. When it comes to the N, it's actually 1 less, as we said, because you have it's on the third shell. You're going to see that when we get to the periodic table. D, and then can go up to 10. And when it goes to the F, it's always N minus 2, and then F to the 14. This is very critical, very, very critical. So again, D is always 1 less than the period number, and F is 2 less than the period